to approach it. So it says, 2 students throw 2 rocks horizontally up a different cliff with different velocities. Sounds kind of like what we talked about yesterday, right? Wow. It says both rocks hit the water at the
same time.
Holy cow, it's not a surprise anymore. But rock B hits further from the base of the cliff than rock A does. It says use the coordinates where up is positive and away from the cliff is positive, and the origin at the top of the cliff at the point of release. Now, the task for you is to, I'm going to zoom it out so you can see what it looks like, and then maybe if I can, oh, there we go. Looks like this. So you're going to draw 4 graphs. Acceleration versus time horizontally. Acceleration versus time vertically. This is all for rock A. And then horizontal versus time. Acceleration horizontal versus time. And acceleration vertical versus time for rock B. Okay? So I want you to get started on this. Have a quick conversation so that we're ready to go. Okay? Go team.
Let's have a quick conversation.
Going. Let's do physics. All right. So show me your boards. I think I want to make sure that we're all doing rock A. Is that correct? Okay. So rock A, I'm looking for the horizontal and vertical acceleration versus time graphs. Show me your boards. Okay, so we did some nice job labeling things. Good job. So I'm seeing that it looks like this for the horizontal. Before I move on, I just want somebody to explain to me why this is 0. Go.
Because there's no jetpack.
No jetpack, no parachute, right? Nothing speeding up or slowing down. So it's got to be acceleration of 0. Fantastic. All right, and then the vertical one, I'm just looking to make sure that I'm getting it. And just sometimes it's kind of hard to see. Okay, gotcha. Okay, I thought I was looking at 2 graphs there. Okay, I get it. Something like this. Is everybody okay there? Yeah? And why? There is an acceleration. Happens to be acceleration due to gravity as the Earth is pulling on the rock or whatever it was, right? And the value of it is what? Negative 9.8 meters per second squared. Okay, looks like that. All right, go ahead and put your boards down. And then will you please graph your graphs for rock B?
Oh.
And Spencer, are you lamenting something over there?
Yes.
Okay, can you just explain to me what you're lamenting? What's so sad?
I erased it.
He erased it, but I asked you to draw for rock B.
Just kind of, you know what we did?
Oh. Not that she's like modest or anything. You know what we did? She just changed it. So like literally what you did, I'm assuming, is went like this, right? Is that true?
Yeah.
Is that what just happened? Okay. Why is it the same? It's a different rock. Look at the trajectories, friends. They're different. So?
Which is not being reflected on the graph.
Oh. The only thing we have is acceleration. And time. We okay?
Yep.
Squared?
No.
Okay. All right. So yesterday we worked on this problem. The tiger leaping off of the cliff. Yes? Okay. We didn't quite get all the way through it, and I want to make sure that you really understand it. So we're gonna jump back in and make sure that we've got it. So please pull out a calculator if you don't have one out. Go ahead and pull your notes out as well. We're gonna just jump through and do this. You did have some homework last night that looks similar to this. I'm not going to go over homework questions today. I will go over them tomorrow. So if you have questions on the homework, bring them tomorrow. And yes, by the way, you do have more homework for tomorrow. I don't know if I mentioned that to you. Do you need to see it or you got it?
I got it.
Sweet. You guys are awesome. All right, here we go. So tiger leaps horizontally from a 6.5 meter high rock, speed of 3.5 meters per second. How far from the base of the rock will she land? I feel like, did we get further than this or no? Is that as far as we got?
Yeah, we finished.
Oh, did we finish this one?
Yeah.
Oh, I copied this from the other class.
Yeah, it was what I did. And like
You got the time. Did we find out how far she went?
4.04.
Oh, good for us.
Oh,
Let me
sorry,
just write that down. That's okay.
4.04, but I used
1.15 seconds. And then that resulted in a delta X of, what was it, 4.04 meters? Okay, so now my question is, that's fantastic. Hopefully everybody's okay with that. If you're not, you can watch the video from yesterday because we did it. How are we feeling about this problem?
Good.
Good? Okay, so I have another one that's like this. that I'm happy to go through if you would like it, or we can just move on. How are we feeling?
I think we can move on.
Move on?
We're doing more content today.
Yeah. We got more stuff to do. I just want to make sure. I didn't want to leave anybody in the lurch. Okay. So we have spent time right now starting projectile motion, looking at one of the 3 types of launches. So I want to write down the 3 types of launches right now. So this would be it's going to take, I don't know, a third of a page in your notes. So if you need to switch to a new page, this would be the time to do it. Okay, so these are 3 types of launches. Type number 1, or letter A, we'll call it. Okay? Letter A is the one we just did. That's the horizontal launch. Horizontal launches generally involve some sort of cliff or building or similar. And the object starts off at the top and then follows a trajectory like this. I'm going to make that a little bit bigger so we can see it. Okay. The initial velocity, VI, is only in the x direction, which means that VIY is equal to 0. Okay? The initial velocity is only in the horizontal direction, hence horizontal launch, right? That's why I named it that. Okay? Taking a look at the other pieces, just to make sure that this all makes sense. This is my delta x. Sometimes in problems, delta x will be called the range. Just means how far did it go? Okay? And then delta y, for these problems, these horizontal launch problems where we are on some sort of cliff, that delta y is always negative.
I need to remember that.
Okay? It's good to know, right? That's why we're talking about it. Yeah. So if we set up our little patented carbon projectile motion givens chart, right? We're going to have delta x, vx, ax, delta y, vy, ay, and then t, the thing that holds it all together. Just a friendly reminder of the things that we know. This is negative 9.8 meters per second squared. Vy, we just said, is what? The initial velocity is, what'd you say? I thought I heard somebody say it. Maybe I was dreaming. 0. Yeah. And delta y, we don't know what it is, but we do know that it's negative. Do we know ax? It's 0 meters per second squared. The vx is just going to be whatever that initial velocity was. And delta x is often what we are looking for. Not always, but often. Okay? That's the one we mastered. That is one of 3. We're going to do letter B next. I don't know what to call letter B, so you guys can help me out. Letter B is generally, well, I'll tell you what I might call it. So here's my object. And now my object is going to start on some sort of level field or playing surface. It's going to go up and come back down. So you can think hitting a golf ball. You can think kicking a soccer ball. You can think kicking a football. Something where it's starting on the ground, going up and coming back down to the ground. Okay? The kick launch?
Sports ball motion.
Well, it's not always sports though, right? Because the next one is going to be like the volleyball serve, right? So we got to get there. We're not there yet. That's going to be level C. So the kick launch, okay. Doesn't have to be kicked, but it gives you kind of a sense, right? It's going to go up.
Parabolic.
But this one's parabolic too.
Total parabolic.
I mean, it could go down. I mean, I'm just playing semantics now. All right, so it's going to go something like this. Yes? Is that okay? That looks like more like a parabola to me. There we go. Fix it. Nope, that one did not look acceptable to me. I was kind of pulling a little loosey there. All right. So what do we know? We know some interesting things about this. So generally, oh, hi. What just happened? We're sorry for crashing. I'm sorry too.
Nice.
Whoops.
What?
I don't think
That's Buhajila.
Click
Click
enter.
here or press
Oh,
enter.
click. Okay.
Yay.
Oh, it just didn't like it when I erased that line. I'm glad that I have you guys to read things for me is what I'm glad. So I was like, what? Oh, I didn't say. Okay, there we go. Now we happy? You still like this page. It's okay. All right. So generally when I draw this, I'm going to draw whatever my surface is. I'm going to draw my object. I like to draw the trajectory just because it's helpful. And then the next thing I often draw is my initial velocity vector. Remember, the initial velocity vector is just going to follow the trajectory. So now this is the interesting part, right? Because now instead of the launch happening horizontally, the launch is happening at an angle, right? So this is the interesting part. This is where we're going to knock out, or bring out, I should say, our trigonometric brilliance.
Yes.
You've got this, okay? So here's the thing, is that this initial velocity happens at an angle. So generally it would say something like the ball was kicked at 5 meters per second at an angle of 22 degrees above the horizontal. That's the kind of thing it would say. So what does that mean? It means that we can take this initial velocity at an angle, and remember, we just want to break stuff into x and y. Because if we can make it an x and y, life is good. That is exactly what we're going to do here. You've done this before, I'm sure. You may just not realize that you've done it. So I've got an initial velocity in the x direction. Are you with me there? Is that okay? And believe it or not, an initial velocity in the y direction. Okay. So I've got my nice little angle here. I'm going to call that an angle theta. And then I'm just going to take a look at that and remind myself that x and y are always perpendicular, which means that I've got myself a really nice little right triangle. Yeah? And so, as I said before, it says something like it's going at 5 meters per second at an angle of 22 degrees above the horizontal, which means that I know theta and I know initial velocity. That's my hypotenuse. So I can find each of these, right? So katoa. Is this sounding familiar to you? Yeah, you got this. You got this. So we're just going to remind ourselves. So some of you are like, I totally got this. Some of you are like, it's been a while and I kind of forgot. It's been a long time. So SOHCAHTOA, SOHCAHTOA. Yeah?
Yeah.
Okay. So if I want to find VX, I have to figure out what VX is. VX is the what? Is it the hypotenuse, adjacent, or opposite side for this triangle?
Adjacent.
It's adjacent. It's right next to, right? So adjacent, and then I've got VI. That's the hypotenuse. Adjacent and hypotenuse, that gives me sine, cosine, or tangent. Cosine. So here we go. So we're going to do cosine. So this is going to be the cosine of theta is equal to VI x over VI. Is that okay with everybody? Anybody mad at me yet? Not so much? Hopefully not. What's that?
Will we eventually become there?
I hope not.
Okay.
Some people just have like anxiety when it comes to trig, and so I just want to make sure everybody's in a happy mood. Okay, so then we can also do, if I want V, okay, but then I just want to solve this too, right? So if I want to get VIX all by itself, that's just going to be VI times the cosine of theta. And I want to be very clear with you, you do not need to memorize this. If you needed to know it, you could figure this out, right? And you may or may not have noticed or recognized that on the AP physics equation sheet, it has your little 90 degree right triangle, and it's got sine, cosine, and tangent on there for you. So if you like are having a total brain freeze, like I don't remember, it's like it's there for you. Okay, it's right there. Okay, so then we can also do VIY. VIY is going to be the opposite side. Opposite hypotenuse, we're going to use which trig function?
Sine.
Sine. Look at us. Sine theta is equal to VIY over VI. Bam, so we got VIY is equal to VI times the sine of theta. Okay. We don't need to do tangent today. Because all we wanted to know is these two things. Because now, and I'm excited that you're excited about that. That's great. But let's just take a look, because now we're going to just draw our nice little givens chart. So I've got delta x, VIX, AX, delta y, VIY, and AY. And the thing that holds it all together is time. Let's take a look and see how much we can fill in here. So delta x, we don't know that. That's the range. That's this distance here. Delta x, again, also known as the range, right? Often watching football, when the kicker comes out, they're like, this kicker's range is blah, 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 right? That's just how far they can kick the football. That's all it is, okay? The initial velocity in the x direction, well, we just find that out, was vi times the cosine of theta. Hey, what's the acceleration in the x direction? 0. We know that every single time. Now, if we're talking about the ball going up and coming back down, don't overthink it, friends. Going up and coming back down, what is the change in position in the y direction? Goes up and comes back down to the same level, right? Delta y, if we're talking about the whole launch from launch back down, just a little friendly note there, because not always that, but usually, then delta y is equal to 0, okay? VIY is VI times the sine of theta. AY is, what did you say, Spencer? -10, yeah, exactly. Okay? And now you've got everything you need to know.
What are we calling this one?
I don't know. I knew you were going to ask. I literally knew. I was like, Elizabeth is going to ask me now what we're going to call it. I'm going to say launch at an angle. Is that okay? Kick launch. You can also call it kick launch if that makes you happy. All right. That's A, that's B. Letter C is simply a combination of the two. Okay? So letter C is a pitcher pitching a ball. Letter C is a volleyball player hitting a ball that then eventually lands on the ground. Letter C is launching some sort of thing off of a cliff at an angle. Okay, so here's the object, and instead of going straight, now it's going to go up and come back down. Okay, same stuff. And all we're doing, so here's my initial velocity, and I have to break my initial velocity into an x and y piece. I'm going to use the same setup. It's all the same thing. It's just that unlike letter A, where VIY was 0, and unlike letter B, where delta y is 0, we have numbers for everything, okay? In general in AP Physics 1, now don't quote me on this, and if something happens in May where this is not true, don't be like, it's crumbling. But in my experience, doing calculations for A and B may happen. It's probably not, but may happen. I wouldn't imagine that letter C, you would have to do calculations on a big scary AP test, okay? But they may ask you to describe the acceleration or describe the velocity or graph one of them or something like that, okay? But so I want you to be aware of this and know that you have to break it up. But solving these problems is not that hard. Sometimes you have to use a quadratic formula. But besides that, it's all good, okay? We good so far? Okay, I'm going to give you a little thinker problem and then we'll do an actual problem. I'm thinking now. Nope, I want to do it this order. I was just trying to decide which order I wanted to do. I think I want to do this. Okay, here's the situation. Speaking of things being thrown. So, baseball projectile motion. Velocity versus time and acceleration versus time graphs. A baseball is thrown from point S in right field to home plate. Okay? The dashed line shows the path of the ball, the trajectory of the ball. It asks you to use a coordinate system with a positive vertical direction. Positive is this way. And the left as positive. Why? Just so that it's easy because it's being thrown from here this way. So we'll just call that positive. Okay?
Right.
What's your, what? I don't know. Because they want to make sure that you can think outside the box, right? Yeah. Now, I'm going to show you just for real quick. There are a bunch of graphs down here. Whoa, look at all those graphs that you're going to get to pick from. But before you do that, because that's overwhelming to me, I want you to think it through. I would like you to sketch these 4 graphs. And friends, it's not that scary. You just got to turn your brain on. You can do this. Horizontal velocity versus time graph. Horizontal acceleration versus time graph. Vertical velocity versus time graph. Vertical acceleration versus time graph. Just sketch them out on your paper real quick. Then I'll show you the choices, and then you can play the matching game. Okay? This is a more efficient way to do it. Also less overwhelming, I think. All right.
Answers.
Coming back. Have you met me? Am I going to tell you the answer?
No, but I need
Of
the
course
answers.
not. Let's figure it out. Okay, so which of these four is the easiest to figure out?
The gravity one. Or
Three.
acceleration. All of them.
Right, so like 2 and 4 are really just like the warm-up problem, aren't they? Same. Okay, so let's do number 2 first. Horizontal acceleration versus time graph. Which one did you choose? Okay, everybody okay with that?
Yes.
Okay.
It's on freeze.
Oh, you can't see. There you go. Oh, don't leave. No. But okay, good. Okay, so see, everybody's good because it's not accelerating in the x direction. Everybody's happy? Fantastic. All right, let's do number 4. 4 says a vertical acceleration versus time graph.
That is gonna be B.
That's going to be B. Why?
Because it's negative and it has a constant acceleration.
Negative constant acceleration, right? Negative 9.8. Bam. Fantastic. All right, so 2 down, 2 to go. All right, so now we're just going to think this through. If C is the horizontal acceleration versus time graph, that means the acceleration in the x direction is always 0. That means that what do we know about the velocity? It's not changing, it's constant. How many of these choices do we have then?
One. Wait. No, sorry.
2, I think, right? Like, I mean, maybe there's just one obvious one. None of these down here, right? Not this one.
Yeah.
Because you got to have a constant. Is the velocity 0 in the x direction?
No.
No, because it's moving, right? Just like a buggy, it's just going. Is it going positive or negative?
It's going negative. Wait,
We're calling left. Let's look.
It's going towards the origin.
We're calling left positive. It's moving to the left. So let's take a look here, friends. If we're going to break this down, so if I was going to draw my velocity vectors, and you might want to do this too, just because it's kind of interesting, right? So your velocity vectors look kind of like this, right? And that's partially because you got x that are like this, right? These are supposed to be all the same length. They didn't really turn out that way, and I apologize for that, okay? We're calling that the positive direction? So what's the right answer here? It's A. Is that a happy face? Okay, cool. All right, vertical velocity versus time graph. So let's just look at it. Don't overthink it. Let's just look at our vectors. So the green vector is the total. The pink is the x. So which way is the y pointing? Up. Do we agree? So it's pointing up here. What does it look like here? It's at 0. Let's put one in the middle just for kicks. In this case, the pink is still the same. The blue one is still going up because the velocities go zoop. Is that okay? Is that making sense? So we can put them together. This one's like this, zoop, zoop, and then you go, yeah? How are we doing? We okay?
Yep.
Yeah? Okay, so it's big, littler, what's it here? 0. These are positive, 0. Tell me about the end. It's negative, and it's getting more and more negative. So it starts off big and positive, smaller and smaller, and then it gets bigger and bigger. Let's figure it out. Which one is it?
Oh, it's I can't read.
So, Hannah, you were just like very adamant that it was I. Why?
Oh, because it's the only one that crosses the x-axis in this straight line.
Oh, okay.
Okay.
Yeah.
I could be wrong.
No, I mean, you could be wrong, but it starts off positive, and it gets slower and slower and slower and slower, and it gets to 0, and then it gets faster and faster and faster in the negative direction. Yeah. It is on. Yeah, good for you. Yay.
Yay.
Go team. All right.
But I can't match.
How are we doing? Are we okay? It hurts your brain?
Just class that.
I'm so glad. Like, the fact that you just said that, just like, oh, man,
It does.
makes my day. Makes my week, perhaps, even. All right. No. We got another 10 minutes. So I need you to stay with me here. I'm going to take a look at this problem. Here it comes. You do. In like 5 minutes. Chill out, dude. A football is kicked at an angle of 37 degrees with a velocity of 20 meters per second. We're assuming the ball leaves the foot at ground level. Ignore air resistance and the rotation of the ball. Calculate the time of travel, how far away it hits the ground. So here, this is looking for t, right? How far away hits the ground? What are they looking for there? Delta x. Change in position in the x direction, the range. We're going to do those two real quick. These other ones here, I'm going to record this for you guys again later because we're not going to have time to do all of it, but I do want to set it up so you can do your homework tonight. So here we go. Patented projectile motion given start. Here it comes. X stuff. Delta X. VIX. AX. Delta Y. VIY. AY. And the thing that holds it all together? Time. Okay? So I'm going to draw myself a picture because I don't really know what's going on. We've got a football. There it goes. It's going to go up and come back down. Something like this. Okay? There's my delta X. Here's my initial velocity in this direction that I can break up into part in the X direction and part in the Y direction. This is the hardest part, friends. If you can do this, the rest of it's golden. Okay? If you can do that, the rest of it's golden. So there's my angle. And here's my initial velocity. Okay? Let's go ahead and get it started. So delta X, we don't know. That's a question mark. VIX is going to be VI times the cosine of theta. So in this case, it's going to be 20 times the cosine of 37. Hey, what's AX? Every time. What's the change in Y?
0.
Goes up and comes back down? 0. VIY. Again, we're going to do just the sign now, right? Just that, what they call component. So, oops. Got excited. VI times the sine of theta. So that's 20 sine 37. What's the acceleration in the y direction? Just like always, right? Okay. We're going to use the y stuff to solve for time. That's question A. Use that time plugged into the x stuff to solve for the change in position in the x direction. Okay. Go ahead and set that up. I'm going to pause right there and start getting my test stuff organized. Okay. As I said, I will record this whole solution again this evening and I'll post it so you can see it as well. Okay. But I think you have enough information at this point to know kind of how to proceed on these problems.